Have you ever looked out over a massive, bustling city and wondered how it doesn't just instantly collapse into chaos? Well, today I want you to completely change how you view your hometown. I want you to stop looking at it as just this random collection of concrete buildings and asphalt roads. Instead, try viewing the city as a massive, living, breathing organism. Every street, every underground pipe, every park, they all play a biological role in keeping this giant creature alive. And today we're really going to focus heavily on the lifeblood of that organism, its water systems. Okay, let's dive into this explainer and dissect the invisible anatomy of our urban world. So here's how we're going to map out this urban anatomy today. First, we'll look at the city's water supply, then managing waste and sanitation. From there, we'll explore planning social infrastructure, housing the population, moving the city through its transport networks, and finally, how we design the whole thing using digital tools.
All right, part 1, the city's water supply. Think of this as the circulatory system.
If a city is a living organism, water is absolutely its lifeblood. It's the circulatory system keeping everything functioning. But actually managing this flow, it is an incredibly complex balancing act for urban planners. Think about your own daily routine for a second. Showering, cooking, drinking, flushing. If you had to guess the absolute minimum daily water requirement for a single person living in a modern city, what number would you come up with? Just take a quick second to think about it. Well, the magic number is 135, specifically 135 liters per capita per day. To put that into perspective, that is roughly 450 cups of coffee worth of water. According to standard urban guidelines, if a city has a piped water supply and a planned sewerage system, planners actually have to guarantee 135 liters for every single resident every single day. And if you happen to live in a massive metropolitan megacity, that number bumps up to 150 liters. Delivering that exact volume to millions of people simultaneously requires some seriously brilliant subterranean architecture. And that brings us to how this water actually travels. It's fascinating because the physical, above-ground layout of your city directly dictates the plumbing hidden right beneath your feet. For example, older, sort of unstructured, organically grown cities might use a dead-end system. It's cheap to build, sure, but water can actually stagnate at the ends of those pipes. On the flip side, if you look at a perfectly planned rectangular city like Chandigarh in India, they use a gridiron system. The water circulates freely without ever sitting still. Then you've got the ring system, which wraps around the city for high reliability, and the radial system. This one is super clever. It pumps water to a central elevated tower and just lets gravity do the hard work of pushing it outward. Moving on to part 2, managing waste and sanitation, which is really about how the city flushes its system. Because look, if the water supply is the arteries bringing fresh lifeblood in, sanitation is the venous system flushing the toxins back out. Without this, the organism literally poisons itself. Now, historically, cities used what's called a combined system. This basically meant the rainwater from a massive storm and the raw sewage from your bathroom went into the exact same underground pipe. The problem there? When it rains, the sheer volume of water is so massive that treating all of it becomes incredibly expensive. Or worse, the whole system just overflows into the streets. Today, the modern standard is the separate system. Planners build 2 entirely distinct networks. Stormwater gets safely channeled straight into rivers, and the domestic sewage is routed directly to specialized treatment plants. But how do we actually know if those treatment plants are doing their jobs? Well, we look at BOD, or biochemical oxygen demand. This is a vital metric for environmental engineers. It basically measures how much dissolved oxygen microscopic organisms need to break down the organic waste in the water. So the really crucial takeaway here is this. A high BOD means the water is highly polluted because the waste is literally starving the water of oxygen. It's essentially the blood test we use to measure exactly how sick a city's water might be. Of course, not all waste can just be flushed away down a pipe. Solid waste requires a very strict hierarchy of management, and it moves from the most preferred action down to the absolute last resort. We always want to start with prevention and reduction. Just make less trash. Next up is recycling, followed closely by recovery, which usually means turning waste into usable energy. And at the very bottom, the absolute least preferred option is disposal. We're talking sanitary landfills. Urban planners despise landfills because they take up massive tracts of valuable land, and they pose a severe risk of generating leachate. Leachate is this highly toxic liquid garbage juice that can seep down into the earth and completely poison the very groundwater systems we were just talking about.
To actually enforce all these sanitation standards, initiatives like India's Swachh admission have rolled out some incredibly strict urban certifications. It starts at ODF, open defecation free, and scales up from there. But the absolute holy grail of urban sanitation is the Water Plus certification. Earning this means a city doesn't just manage its solid waste and its toilets, it ensures that absolutely all of its wastewater is treated to a satisfactory level before a single drop is discharged back into the natural environment. The city of Indore famously became the first to achieve this, completely proving that a perfect, closed-loop harmony in a city's water cycle is entirely possible. Section 3. Planning social infrastructure, or as we're calling them, the organs of the city.
Okay, so now that our circulatory system is flowing with clean water, we need to build the vital organs, the schools, the hospitals. You might think planners just sort of build these wherever there's an empty plot of land, but urban planning is an exact science. According to the URDPFI guidelines, these organs are strictly tiered based on what's called a catchment population. Look at this table. A neighborhood only needs about 2,500 people to get a pre-primary school. But to justify building a full-degree college, you need a population of 1.25 lakh. And for a massive multi-specialty hospital, planners won't even sanction one unless there's a catchment of 10 lakh people ready to be served.
But why are these numbers so rigid? Why not just build a hospital everywhere? Well, it all comes down to a geographic concept by Walter Christler called threshold population. It's pretty simple. It's the bare minimum number of people required to economically support a service. If you build a massive, state-of-the-art hospital in a town of just 10,000 people, it won't generate nearly enough use to pay its doctors or maintain its expensive equipment. The organ will simply fail. Understanding this economic threshold is exactly how planners perfectly and efficiently space out services across the entire city map. Part 4. Housing the population, the tissue of our urban organism. Surrounding all those organs is the tissue of the city, the neighborhoods where citizens actually live. And when planning this housing, especially affordable housing, precision is everything. You've probably heard real estate terms thrown around that can be, quite frankly, incredibly confusing. But the golden rule today, which is legally enforced by the RERA Act, is carpet area. This is exactly what it sounds like. It's the actual usable space inside the walls of an apartment, literally the area where you could lay down a carpet. Developers used to sell properties based on super built-up area, which unfairly charged buyers for shared lobbies and staircases. By strictly defining carpet area, the government can step in and mandate that, say, economically weaker section housing provides exactly 30 square meters of actual usable living space. And this kind of precision is absolutely vital for upgrading the city's most vulnerable tissue, its slums. Historically, the global approach to slums was aggressive clearance. Cities were literally just bulldozing neighborhoods. But today, under modern missions like PMAY Urban, the preferred strategy is ISSR, or In Situ Slum Redevelopment. This is a game changer. Planners use the land itself as a financial resource. Private developers come in and build modern, multi-story housing for the residents right on a portion of their original land. It provides them with proper plumbing, safe structures, and clean water, all without displacing their communities or destroying their local livelihoods. Let's move to Section 5. Moving the city, the transport networks, our urban arteries. Now, of course, all this housing and infrastructure is completely useless if people can't actually move between them. To design these transport arteries, planners have to measure traffic, but here's the catch. A motorcycle doesn't take up the same space as a massive delivery truck, right? So how do you measure road capacity? Enter passenger car units, or PCUs. This is how transport planners solve the math problem. They convert every single vehicle into a standardized unit. A standard car is baseline 1.0. A two-wheeler is 0.5. A big bus? That's a 3.0. By running these conversions, planners can calculate the true, standardized capacity of any road, regardless of what's actually driving on it at any given moment. But you know what the biggest choke point in these arteries actually is? It isn't moving cars, it's stopped ones, parking. Planners measure parking using equivalent car space, or ECS, and on-street parking is an absolute nightmare for urban flow. It eats up incredibly valuable road capacity and causes massive rippling congestion. That is exactly why modern cities are starting to price street parking incredibly high. The whole goal is to force drivers toward off-street parking, like multi-level car parks or underground garages, keeping the main arterial roads completely clear for smooth transit. And finally, Section 6, designing with digital tools, the brain of the city. So with all these complex water systems, social catchments, and traffic flows, how is all of this actually coordinated? Through the city's digital brain. And the foundation of this brain is BIM, or building information modeling. Think of this as looking at the exact cellular makeup of a single urban organ. If planners are building, say, a new metro station, BIM provides a microscopic 3D view. It doesn't just show them what it looks like, it tells them exactly how many steel rebars are required, the exact volume of concrete, and exactly where every single internal water pipe needs to be routed.
But BIM is just one piece of the puzzle. Let's zoom out and see how this builds into the bigger picture using GIS, or Geographic Information Systems. While BIM is very micro, GIS is completely macro. It takes that highly detailed 3D metro station we just talked about and drops it into a real-world geographic context. GIS tells the planners if that station happens to be sitting in a high-risk flood zone, exactly how it connects to the nearest arterial road, and how the city's wider water supply network will interface with it. And here is where it gets really cool. When you combine the microcellular details of BIM with the macro environmental data of GIS, you get something truly futuristic: city digital twins. These are highly accurate, entirely virtual replicas of the physical city, and they are updated constantly using real-time data from Internet of Things sensors all over the town. Before a city even pours a single ounce of concrete for a new highway, or say a new water treatment plant, they build it in the digital twin first. They can simulate exactly how traffic will organically reroute, where air pollution might spike, or, crucially, how water pressure will be affected across 1 million different homes, all inside a safe virtual sandbox. We've traced the city from the water pumping through its underground veins, to the organs providing social life, all the way up to the digital brain, simulating its very future. As these digital twins map every single underground pipe and arterial road, it becomes so clear that the city is no longer just a static pile of concrete. It is a highly dynamic, beautifully engineered ecosystem. So knowing how this invisible anatomy works seamlessly behind the scenes to keep you and millions of others alive and thriving, how will that change the way you see your own neighborhood when you step outside tomorrow? Thanks for exploring this explainer with us, and as always, keep questioning the world around you.